All right, so today we're dealing with the fundamental theorem of calculus. That is ugly. Okay, fundamental theorem of calculus, and this is the basic idea. Okay, basic idea. If I take the derivative of a problem, if I take the derivative of a problem, sorry, give me one moment. Okay, from some value a to x of f of t dt. So we're changing this letter. This is a t here, okay? Be aware of that. This is equal to f of x. Okay, fundamental theorem of calculus. Okay, looks super confusing, looks a little annoying. But the idea is, what if I ask you to take the integral of something and then take the derivative of it? Okay, it's like, what if I ask you to multiply by 2 and then divide by 2? Shouldn't you kind of end up where you started from? Right? So this is our starting point today. And why do we do this is because we'll see problems where we have to take the derivative, d over dx, of the integral of, let's say, 3 of 2x, or 3 to x, of making it up. Let's say it's 3, no, let's not use 3, let's use 7t plus, oh, let's just stick with this. Super easy. Okay. Now, I'm asking us to take the derivative of an integral. So essentially, they should cancel each other out. But let's actually work this out. If I say this is d over dx of, okay, let's take the integral of 7t. That's 7t squared. Oh, I don't know why I wrote it that way. 7t squared over 2, right? And then we're going to plug in x and 3. Everyone okay with I just did power row? Okay. And then if I plug it in, we're still taking the derivative of plugging in 7. T becomes an x squared over 2 minus 7 over 2 of 3 squared. Is that kind of on board here? Okay. What I did was I just plugged in the x and the 3, right? F of b minus f of a. Okay. Hopefully you guys are all on board still. And now, once we're done here, you can come up with this is some number. Okay, that's some number. Fy, that's some number, some constant number. But what if I ask you now to go ahead and take the derivative of the same exact problem? Take the derivative of the same exact problem. The derivative of 7 over 2x squared, it's 7, sorry, that's not 7. 7 over 2, 2x, right? That's the derivative. And what's the derivative of a constant? 0, right? So we're left with 7x. So what is the derivative? Coming back here, it's just 7x. Okay. So here is the fast way of looking at it. If I'm taking the derivative of an integral with the variable on top, just plug in the variable. Because what does a derivative and an integral do to each other? They essentially cancel each other out. But what about this constant? Well, take a look what happens to any constant when I take the derivative. What happens to any constant when I take the derivative? It just goes to 0. It's going to go away anyways. So if we come back up here to our initial rule, where a is a constant, here's a basic rule. If I'm taking the derivative of an integral of a function, whatever that function may be, just take the x and plug it in. Because if I did all the work anyways, it's really just going to be undoing that integral with my new variable. Okay. So let me go ahead and give you guys another example. If I write d over dx of okay, we don't need to write the parentheses, but the integral, okay, of e to the 7x plus 1, sorry, not x, I'm sorry, 7v plus 1 dv from 764 to x. Okay, can you give me a guess of what the answer could be? Why don't you guys just give me a guess if you guys can able to guess that, following our previous rule without doing any of the work. You could no work here. The rule simply states, let me go ahead and review the rule. The rule says if I'm taking the derivative of an integral, they should essentially cancel each other out. So just plug in the variable into your inside variable, let's call it. Okay, so hopefully you guys should see this is simply just e 7v. V becomes what? V becomes x plus 1. Thank you. And we're done. That's it. What happens to the dv? Remember that it was taken out during the integral. And then what happens to 764? Well, that's going to give us a constant, and the derivative of any constant is back to 0. Okay. Okay. Is it really that easy? Is it really that easy? Okay. Well, yeah. If it's that easy of a rule, let me give you another one. d over dx of the integral of a, which can be any constant, okay, any constant, and to x of 1 over 1 minus x squared dx. Oh, sorry, darn it. I always do this. I always write x's too much. We're so used to writing x's. Letter q, okay? Q squared dq. Okay? Dairy Queen. Alright, so go ahead and plug that in. What do you think your answer is going to be? It's simply going to be 1 over 1 minus x squared. Okay. Now, why is this true? Is because, like I showed before, if I went through the work of taking the integral, right? After we take the integral, don't we always plug in the top minus the bottom? And the constant bottom will always go to 0. It will always go to 0. And what happens with your integral, if I take the derivative, it just brings you back to your original problem. So we were just going to undo the integral anyways. Undo that integral anyways. Okay. Great. Easy peasy. Now, the next question is, what if I had two variables here? What if I had two variables? What if I wrote d over dx, the integral of, let's say, from x to 2x, okay, of, let's give ourselves something easy, 3t dt, okay? Now, there are a couple of rules for integrations that I didn't really super cover. And one of the rules for integration is this. So let's go take a break here. We'll come back to this problem. And the rule is this. Given some value, I'm going to give you guys a basic rule. If I say 1 to 5 of f of x dx, okay? We mentioned before that integral is area underneath the curve. So I'm just giving you guys a dumb graph. And here's my dumb graph from 1 to 5. Okay, 1 to 5. Could I break this graph into smaller parts? Does it have to be straight from 1 to 5? Could I break up this trip into smaller trips? What if I want to say, I want to break up this trip instead from 1 to 3 and then continue the trip later from 3 to 5. Would that be okay? Would that still give me the same answer? Right? If I go from 1 to 5, right? This is up here, that's 1 to 5. That's the whole trip. Instead, what if we add our two smaller trips where we take a break in the middle? Would they give me the same answer? Ideally, it should, right? And here's one of our rules for integration, is that you can always separate our integral. Now, let me give you guys this idea. The integral from a to b of f of x dx can equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx, as long as c is between a and b. Right? So here's one of the cool things, that we can always separate an integral into multiple parts, right, along the way. Here's another cool thing. Imagine if I gave you a graph, and one graph is up here, and the other graph is down here. Okay? And the graph, this is y is equal to, let's say, 3. And the other graph is, call this 2. Y equals to negative x plus 4. Wait, oops. Y, that's 3. 3 plus 5. Okay. So that's this equation, and this is this equation. How can I find the area underneath the curve? This could be two different integrals from 0 to 2. That is the function of 3. My second integral is from 0, sorry, from, let's call this, from 2 to 5. So I wrote this full integral is just a sum of two separate integrals. Okay? So this is the integral of, let's say, from 0 to 5 of f of x dx, where f of x is a composite function of 3 when x is between 0 and 2, and negative x plus 5 between 2 and 5. Okay, so if you take a look at what I wrote here, is I said I want the integral of this function here from 0 to 5. Well, from 0 to 5 we have two different equations. From 0 to 2 the equation is 3, right? That's 3. And from 2 to 5, the equation is negative x plus 5. So the point of this is I can always separate my integrals into different stages, right? Wherever I want to stop. Now, why is this important to me? Why am I bringing this up? Is because if I go back up here and look at this problem here, this here does not fit my fundamental theorem of calculus rule. It doesn't. So we cheat it. We actually separate it. We break it up and we say instead, hey, why don't we break this up and say this is the derivative of from x to a 3t dt plus the integral from a to 2x of 3t dt. All right. Now, here is my issue here. Take a look here and take a look here. Which of these kind of fit my model from before? What fits my model from before is the variable has to be on the bottom. If it's not on the bottom, sorry, the variable has to be on top. The constant has to be on the bottom. Now, why is that important for us? Because let's go back and look at my original problem. When I took the derivative, x is on top and the constant is on the bottom. Remember when we take a definite integral, who gets the negative sign? The top value or the bottom value? The bottom value, right? Don't we always put a negative on the bottom value? So here's what's going to happen. That negative sign is going to be important because what happens when I take the derivative of a constant, even though it's negative? It goes away. I don't care. What if I put the variable on the bottom? It actually becomes negative. Let me go ahead and show you guys this. So in order to do this problem, we're going to actually spin this around. And the way we spin this around is that we give it a negative. So here's what we do. d over dx, negative integral from a to x of 3t dt plus the integral of a to x 3t dt. So here's the next thing we have to make sure we understand. What if I have my boundaries spun the wrong way? And the way we spin them around, so let me go ahead and give you guys another rule real quick. The rule is, if, here's my, here's a rule. The integral from a to b of f of x dx is equal to negative b to a of f of x dx. Okay, if you ever want to spin around your a and b value, you can, you just have to put a negative in the front. Okay. It will give you the same exact answer except there's a negative. So that's what I did here. I spun it around with a negative sign.
How does the negative like factor in the problem? You just treat it like a -1 constant and you
Yep.
leave it out.
Just leave it out and just bring it back in at the very end, because a derivative of a constant -1 doesn't change it. Okay. So here we go. If I take the derivative now, okay, now this is still going to be a little tricky, because we take the derivative of this guy, it's just going to be 3x. Don't forget to bring down the negative. Are you guys okay with that? The derivative of an integral, just bring down the variable to plug in the variable. Let's go ahead and do it for the next guy. If I go ahead and take the derivative of the next integral, we mentioned before, this is just really plugging in the variable. But there is a situation here. I want you guys to look at this problem here. Isn't this like, not specifically this problem, but this would have been a chain rule problem. So this is what you need to include. You need to take the derivative of 2x. And the derivative of 2x is just 2. So we have to actually write this -3x plus 2x times 2, because you have to chain rule it. Okay, so I'm going to go ahead and show you guys why we have to chain rule it, just to prove it to you, and then we'll be able to do these problems actually very quickly from here on out.
Wait, Mr. Ko,
Yes.
why are we taking the derivative of that?
Okay, so I'm going to demonstrate that to you right now, okay? So if I write the integral of, let's say, I'm going to give you guys numbers so your brains don't break. And then I'm going to write 2x, and we're going to write like 3t dt. We're going to actually take the integral, and then we're going to take the derivative of this, okay, by hand, just to prove it to you. So if I take the integral of this, we said it's going to be 3t squared over 2, plug in 2x, and plug in 2. And then we're going to take the derivative of this afterwards. Cool with that, right? Now we plug it in.
Yeah.
2x squared over 2 minus 3 over 2. And we're going to plug in 2 squared. And then, need parentheses there. I put the parentheses in the wrong place. Okay. Now, if I take the derivative, do I care about the constant? Goes away, 0. Everyone cool with that? That's why we never care about what that constant's going to be. But what is the derivative of this guy here? The front value would be 3 over 2. Power rule first would be 2 times 2 to the x to the 1 power, right? These are going to divide out, gone. But don't we have to do chain rule now? Then we chain rule. And that's why we need to multiply by that chain rule. The fundamental theorem of calculus is great because you just plug it in. But really, take the derivative of it. And when I take the derivative, I need to include a 2 because of chain rule. Now let me go ahead and show you the quick differences between two easy problems. d over dx of, call it a to x of sine of x dx. Okay? So dang it, okay, I always do this, like no joke, I always do it. Like let's call it t and t. Okay? What happens to the derivative and integral? We say they should cancel each other out. Fundamental theorem of calculus says just plug that in. That's just sine of x. Okay, everyone digest that? Does that make sense? Okay. Again, fundamental theorem of calculus says, hey, these derivatives and integrals should cancel each other out. That's make our lives easy. That's just go ahead and plug in that x value in. If I actually did all the work, if I took the integral of sine and did all that work, we'd still get the same answer. Okay. Now, why do we need this fundamental theorem of calculus? Because do you always want to take the integral? And know what? Sometimes you can't take the integral. We don't know what the integral of that value would be. Okay. So here is the same exact problem now, except with x squared. Okay, we know a derivative and integral cancel each other out. Fundamental theorem of calculus says just plug it in. Sine of x squared. Chain rule, 2x. If you want to make this pretty, write the 2x in the front so we don't get confused. Okay. Why is this true? Let me go ahead and show you guys one more time. The integral of sine is negative cosine. So d over dx, negative cosine t, plug in x squared and a. Right, because the derivative of cosine is negative sine. When I plug in x squared, it'll be negative cosine x squared minus negative cosine a. Do we care about the derivative of a constant? Remember, that's just a constant. We don't care. It was going to go away anyways. So focus on your derivative of cosine. What's the derivative of cosine? That's negative sine. So negative sine of x squared. Chain rule, the derivative of x squared is 2x. This equals to sine x squared 2x. Save yourself some time. Okay, let's make this fugly. D over dx from a to x squared minus 6x plus 2 of tangent of t dt. Can you think of any integral of tangent? Is there an integral of tangent? No. Not that we know of, right? So screw it. We just plug it in. Tangent of x squared minus 6x plus 2. Chain rule, 2x minus 6. That's it. We're done. Okay, so let's go back to our problem that we were finishing up here. So just to talk about this again, right here, we plug it in. That's how come we ended up with a 3 times 2x. The t became a 2x. Chain rule, and then we have to plug in that 2 now. That's why it's 3 times 2x2. Okay, all right. Okay, let's do another problem, one of these types of problems. Integral from 2x to x squared, d over dx. And we're going to say this is secant. Darn it. I'll do it again. Okay, so we did the easy ones. Now we're going to go ahead and do the hard ones. So first thing is, we need to split this because we can't have a variable and a variable. Okay, so let's split it. When I split it, we end up with d over dx integral from 2x to a secant t dt. And then we're going to add this to an a to x squared secant t dt. Why? We're connecting from a to x squared, but with some value in between. Some a value in between. So a is someplace between 2x and x squared. Because we want this constant. The fundamental theorem of calculus says, hey, have a constant, I'll save you a life. Save you some time. We realize that the first part of this equation is in the wrong order. It's in the wrong order. So let's spin it around. The way we spin it out, we just stick a negative in front. D over dx, negative integral a to 2x secant t dt plus the integral of ax squared secant t dt. Is everyone okay with my break? Now, I want you guys to go back to think about what is the derivative of a plus. Remember, if I have a plus sign in my derivative, we treat them separately, don't we? Right? So since we can treat them separately, we can write a dx to both of these separately. Right? We're just taking of them the derivative of each of these integrals separately. I'm not going to rewrite it because there's a lot of writing. So here we go. Let's go ahead and take the derivative. This is going to be negative. Plug it in. Fundamental theorem of calculus. The derivative and the integral cancel each other out. So we just plug it in and get secant 2x. Chain rule. The derivative of 2x is 2. I probably want to write that in the front, make it look a little prettier. Next one. Chain rule. So we have plus secant x squared 2x. To write this a little prettier, negative 2 secant 2x plus 2x secant x squared.